In this lesson today, we're looking at the exponential probability density function. So this is a specific focus from the syllabus, and it says that we need to use and apply the probability density function. Specifically, f of t is equal to lambda e to the negative lambda t when t is greater than or equal to 0. So that means that we're looking at a probability density function that follows an exponential decay relationship. Right, now the parameter lambda must be greater than 0, and that makes sense. That keeps it as a decay, and we need to be able to then use the exponential random variables and associated probabilities and quantiles to model data and solve practical problems. So we'll see how this all works together. So basically, what we're saying is that it will follow an exponential distribution, and that is that it will always follow this rule, lambda e to the negative lambda x, where x is greater than or equal to 0. Otherwise, it will be 0 at any other point. So it cannot be negative. If it's negative, it's 0. And you can see that this is just a standard exponential decay relationship, except that we've got this common parameter as part of the exponent, but also as a coefficient of the function. All right, and that will define the curve. Right, so just a reminder, because in method you've already looked at probability distribution functions. This is a very specific one. So for every probability distribution function, it must be a function of x, which is always greater than or equal to 0. So it must be above that x-axis. The area under the graph must always sum to 1. And for the exponential probability distribution, it is memoryless, which means that regardless of where we start, we're going to consider it from that point. So that probability of x is greater than 5 plus 1 more, given that we're already at that point, x is greater than 5, would just be looking at the probability that x is greater than 1. So what we mean by memoryless is that it does not consider what has happened before. So this 5 minutes that's already passed is not considered when we're solving the problem. We're just looking at the problem from that starting point. So it was 5, we've gone 1 more than that, so we're just looking at that probability that x is greater than 1. All right, so these exponential probability distributions are designed to consider time between the occurrence of random events. In other words, we're going from this point and we're looking to determine the probability of an event happening between that time or beyond that time. It always follows this function, as we've already said, and we can calculate the mean. The mean will always be 1 over lambda, so that parameter we were talking about, and the standard deviation will also be 1 over lambda. Okay, I'm going to prove the mean and the standard deviation for you. Mean and standard deviation, we know that the mean is Ex, which is the integral between negative infinity and infinity of x f of x with respect to x. So you would have used a rule similar to this when you were looking at your discrete probability distributions. So it's a sum of all the products of the probabilities and the number. So in order to find this sum of the continuous distribution, we're going to use an integral. Now, as we know that x must only be greater than or equal to 1, we can say that this is going to be between infinity and 0 of x, and then multiplied by our exponential probability distribution function, which is lambda e to the negative lambda x. So this is all with respect to x. Now this itself is actually a by parts integration. So if we look at this as a by parts integral, we know that u will be equal to x using Lipit, du dx will be equal to 1, dv dx will be our second function, which is lambda e to the negative lambda x, and v will then be the integral of this, so we'll end up with negative e to the negative lambda x, which means that our integral will be uv, which is negative x e to the negative lambda x, subtract the integral, of v du dx, which will make that plus e to the negative lambda x with respect to x. So we end up with negative x e to the negative lambda x, and then subtract 1 on lambda e to the negative lambda x. And so this being our integral, we can say that it is our integral of negative x e to the negative lambda x, subtract 1 on lambda e to the negative lambda x between infinity and 0. Now, there's an issue when we try and sub infinity in, as infinity is not an exact value. So we can look at the limit as k approaches infinity of negative x e to the negative lambda x minus 1 on lambda e to the negative lambda x, and we're between k and 0. Now, when we think about the limit as k approaches infinity of negative k e to the negative lambda k, subtract 1 on lambda e to the negative lambda k, and we subtract our 0, subtract 1 on lambda e to the power of 0, then this should be pretty easy to consider, because when we think about as k approaches infinity, then e to the negative lambda k should approach 0, because as we get larger and larger values in this power, as it's a negative power, we're looking at 1 on that large value. So when we divide by very large values, we get closer and closer to 0. And so that means our limit here for each of these values is 0. So we have 0, subtract negative 1 on lambda, which is plus 1 on lambda, and we can see here that our mean is 1 on lambda. Now, whether you have to replicate that proof is unknown, but it should make relative sense there, and we can use our integral skills quite readily. Now, in order to calculate the variance, which will get us to standard deviation, so standard deviation is equal to the square root of the variance, and so the variance will be the difference between e of x squared subtract the mean e of x all squared. So what we're looking at is the difference between what we would expect the square of the scores to be and the expected outcome, or the mean, squared. Okay, so knowing this is our variance, obviously we need to now calculate what this e of x squared is equal to. So first of all, we need to be able to calculate e of x squared, which is the integral between negative infinity and infinity of x squared f of x, which is the integral between 0 and infinity of x squared lambda e to the negative lambda x with respect to x. Now this as an integral will end up, using a by parts process again, and we'll shortcut this, being negative x squared e to the negative lambda x, negative 2 on lambda x, e to the negative lambda x, and negative 2 on lambda squared e to the negative lambda x. So this is what the integral ends up being. You can go through that by parts process yourself if you like. It will go through 2 iterations, as after the first integral we'll end up with that x f of x. And of course this will be between infinity and 0. So we end up looking at the limit as k approaches infinity of negative x squared e to the negative lambda k, subtract 2 on lambda k e to the negative lambda k, and subtract 2 on lambda squared e to the negative lambda k. And then with a 0, because the first 2 have x's involved, it's 0, subtract 0, subtract 2 on lambda squared e to the power of 0. Now for each of these again, as k approaches infinity, e to the negative lambda k approaches 0, So we end up with 0 subtract -2 on lambda squared, which leaves us with 2 on lambda squared, which allows us to calculate our variance now. Our variance will be 2 on lambda squared subtract the mean squared, which is 1 on lambda squared, which leaves us with 2 on lambda squared subtract 1 on lambda squared, which is 1 on lambda squared. And standard deviation will be the square root of the variance, which is 1 on lambda squared, which of course ends up being 1 on lambda. So again, whether or not you need to know this proof is yet to be determined, but it's pretty easy to work out. Now obviously the integral here and the application is a bit harder, but we can see that we've shown that in all cases with this exponential probability function, the mean is 1 on lambda and the standard deviation is 1 on lambda. And so that sets it up and makes it quite easy to interpret. Alright, so the last thing we're going to look at before we look at a couple of problems is a cumulative distribution function. So that means we're looking to try and determine f of x, which is the probability of x being less than or equal to x, which really is the integral between x and 0 of any function with respect to x. So that is that we're looking at the integral between x and 0 of lambda e to the negative lambda x with respect to x. And that means we're looking at negative e to the negative lambda x between x and 0. So what we've got is negative e to the negative lambda x, and then subtract negative e to the power of 0. So negative e to the negative lambda x plus 1, or 1 subtract e to the negative lambda x. Now this should simplify our process a lot. F of x will always be 1 take e to the negative lambda x. Now I should have clarified this earlier, but the truth of the matter is that the rule for the exponential probability distribution function is not on the formula sheet, which means that you need to know it well enough to be able to recall. So obviously you can remember the function, but also you want to be able to remember this cumulative function because it makes everything much easier. Alright, so that introduces everything you need to know with the exponential probability distribution function. You should have a bit of an understanding of how we're going to use it. We're looking at probabilities between certain amounts of time, and you'll see that in the examples we look at next lesson. Okay, thank you for listening.